bits for encoding. Okay, so how many decimal digits we can encode? When we use 2 binary bits for encoding, then we may have 00, 01, 10, 11. Now this 00 is corresponds to decimal digit 0, 01 corresponds to decimal digit 1, 10 corresponds to decimal digit 2, and 11 corresponds to decimal digit 3. So the value in the range of values are in the range of 0 to 2 to the power n minus 1. Here you see what is n? The small n is equal to 2 because we are actually using 2-bit encoding. That is why small n is equal to 2. So the values in the range of 0 to 3, because 2 to the power n minus 1 is nothing but 2 square minus 1, that is 3. So you see the values are in the range of 0 to 2 to the power n minus 1. So 0, 1, 2, 3. Okay, and when we are using 3 bits, when we use 3 bits for encoding, we may have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So this corresponds to 0, this corresponds to 1, this corresponds to 2, this corresponds to 3, this corresponds to 4, this corresponds to 5, this corresponds to 6, and this corresponds to 7. Here also small n is equal to 3. So 2 to the power n minus 1, it is nothing but 2 cube minus 1, which is 7. So values are in the range of 0 to 7, right? But in case of BCD, which is binary coded decimal, one decimal digit will be encoded by 4 binary digits. In the case of BCD, one decimal digit will be encoded by 4 binary digits. Now, decimal digits. What are the decimal digits? 0 to 9. Okay, so one decimal digit will be encoded by 4 binary digits. So I will write here decimal digits, and here it will be BCD, binary coded decimal. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8, and then 9. And we will do encoding with 4 binary digits. So 0 will be encoded by 0, 0, 0, 0. 1 will be encoded by 0, 0, 0, 1. 2 will be encoded by 0, 0, 1, 0. 3 will be encoded by 0, 1, 1. Sorry, 0, 0, 1, 1. 4 will be encoded by 0, 1, 0, 0. 5 will be encoded by 0, 1, 0, 1. 6 will be encoded by 0, 1, 1, 0. 7 will be encoded by 0, 1, 1, 1. 8 will be encoded by 1, 0, 0, and 9 will be encoded by 1, 0, 0, 1. So that is why the decimal digits 0 to 9 will be encoded by 4 binary digits. Because if you see, when you are using 3 binary digits, you can only encode the decimal digits from 0 to 7, isn't it? When you will use 3 binary bits to encode the decimal digits, you can only encode 0 to 7. But actually decimal digit stands for 0 to 9. So when we are going to encode till 9, then we need 4 binary bits. Because when you will try to encode 8 and 9, for 8 and 9 you need 4 binary bits. Okay, 1000 and 1001. 9. For 8 you have 1000, for 9 you have 1001. So that is why we are using 4 binary digits to encode decimal digits, and it is nothing but the binary coded decimal. And here the interesting thing is that here the small n is equal to 4. 4 binary digits we are using to encode decimal digits. Right? So when small n is equal to 4, so maximum, when small n is equal to 4, maximum we can encode 0 to 2 to the power n minus 1, which is 0 to 2 to the power 4 minus 1, that is 0 to 15. But we have encoded only 0 to 9. So what happened? With rest of the 6 numbers. Okay. When we are using 4 bits, carefully listen. When we are using 4 bits for encoding purpose, we can encode the values from 0 to 15. But in case of binary coded decimal, we are actually encoding 0 to 9. But using 4 bits. So what about 10, 11, 12, 13, 14, 15? These 6 numbers. 1, 2, 3, 4, 5, 6. Because we are using 4 binary bits. So we can encode till 15. But you need to understand what is the code, binary coded decimal. We are trying to encode decimal digits by using 4 binary digits. And decimal digits means it's always 0 to 9. When we are considering 10, 11, 12, 13, 14, 15, these are not decimal digits. These are decimal numbers. These are not digits, these are decimal numbers. We are not going to encode these decimal numbers. So these 6 values, 10, 11, 12, 13, 14, 15, these are the don't care. Okay. This 10, 11, 12, 13, 14, 15, these are don't care. These are don't cares, and it can be denoted by X, 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 X. Okay. I'll show you. Okay, you see, each decimal digit is represented by 4 binary number. Decimal means base is equal to 10, when r is equal to 10. Decimal digits range from 0 to r minus 1, means 0 to 9. Hence, 0 to 9 are the 10 distinct digits we have in decimal number system. 8, 4 to 1 are the positional weights. So, by decimal digits, we mean from 0 to 9. 143 is not a decimal digit, it is a decimal number. 143 individually are decimal digits. 1, 4, 3 are the decimal digits, but when we are combining these 3 decimal digits, we are actually forming one decimal number, which is 143. So these are the decimal 0 to 9, and this is the BCD code on the right hand side, corresponding BCD code. I will talk about 8421 little bit later. Now, invalid BCD code. As we have used 4 bits, the total possible combination will be 16. We have represented 10 decimal digits. What about the rest of the cases? Means 6. Hence, 10, 11, 12, 13, 14, and 15 are the decimal numbers. They are not decimal digits. That we have already, I have explained. So these decimal numbers, 10, 11, 12, 13, 14, 15, these are don't care, because these are decimal number. These are not the digits. We are only representing decimal digits in the BCD, but we are encoding decimal digits by 4 binary digits. Okay, so these 6 are the don't cares. Okay, now we will just tell you (8421) code, right? 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1. (8421) code. You have 0 1 1 0 0 triple 1 1 triple 0 1 double 0 1. So 8421 BCD is weighted code. The positional weights are 8421. Okay. So when I will write 8421, and when I am writing the code, the BCD code, which is 1 triple 0, this is the positional weights. How to find out equivalent decimal digits? You see, positional weight. So how to find out it? Here you see, this 8 will be multiplied by 1, plus 4 will be multiplied by 0, plus 2 will be multiplied by 0, and 1 will be multiplied by 0, and finally the equivalent decimal digit is 8. Okay, so this is the positional weights, and this is the methodology how to find out the equivalent decimal digits. What is the working of positional weights? I think you understood. I will take another example, 8421 code, which is nothing but your BCD code. and suppose it is 0110. The BCD code is 0110. So what is the equivalent decimal digits? 8 into 0 plus 4 into 1 plus 2 into 1 plus 1 into 0. So it will give you 0 plus 4 plus 2 plus 0, which is 6. And you see the 6 represented in BCD by 0110. So you have to multiply the positional weight with the binary number, either 0 or 1. Okay. So you see the in the positional weights actually what we can say that here in case of 8, the positional weight 8, here 0 is present, so 8 will be multiplied by 0. And in the positional weights 4, the binary number 1 is present, so that is why 4 multiplied by 1, and then 2 multiplied by 1, and then 1 multiplied by 0. And if you all add up, if you all add this product, you will get 6. Okay, so this is the positional weight 8421. Now, conversion of decimal number to BCD. How to convert it? 35 base 10 is the decimal number, 3 and 5 are the decimal digits. We know the BCD representation of the decimal digits 3 and 5. 3 is actually 0011, 5 is actually 0101. So the BCD representation of decimal number is actually 0011, 0101. Is the BCD representation of the decimal number 35. Okay, means what is happening over here? 35 base 10 is the decimal number, and this decimal number consists of decimal digits 3 and 5. So the BCD representation of 3 is actually 0011, and BCD representation of 5 is actually 0101. So how to represent 35? You will encode 3 by 0011, and you will encode 5 0101. So this is the BCD representation of 3. This is the BCD representation of 5. So finally 35 base 10 is represented by 0011, 0101. Okay, so this is the BCD representation.
Sir, I have a doubt.
Yeah.
Sir, in the previous example, where did the 8421 come from?
It is the positional weight, it is the name, it is the standard 8421 code. The BCD code is known as 8421 code.
Okay, sir.
Okay. It is
Yes,
not
sir.
my assumption. It is the standard. It is 8421 code. Right.
Okay, sir.
So now 35 can be represented in this way. Now another example, 174 and 2479. So 174 base 10, this is the decimal number. How could you represent it? For 1 you have 0001, for 7 you have 0111, for 4 you have 0100. So the final representation is 0001, 0111, 0100. This is the BCD representation of 174 base 10. Okay, another example 2479. 2479 base 10. For 2 we have 0010. For 4 we have 0100. For 7 we have 0111. For 9 we have 1001. So the BCD representation is 0010, 0100, then 0111, then 100. So this is the this decimal number. Now, BCD to decimal conversion. So this is the BCD number given to you. How could you convert it to the equivalent decimal number? Look, here it is the very important point. Start from right and make a group of 4 bits. Because you know what is BCD. You are encoding the decimal digits into 4 binary bits. So you have to make a group of 4 bits. And you will start from right. So you have 10100. So you will start from this side right, and you will make a group of 4 bits, 4 binary bits. So like this, 4 binary bits, and you have 1. So put another 30 on the left hand side, and you will make another group. So from here you will get 1, from here you will get 4. So it is 14 bits, right? Okay, now comparison of binary and BCD. You see, when you have the decimal 10, you check out the binary 1010 and you check out the BCD. For binary, for decimal 12, what is the binary and what is the BCD, you can easily understand. So in case of binary, we used 4 bits, but in case of BCD, we are using more than 4 bits. BCD is less efficient than binary as it requires more number of bits to represent the same decimal number. BCD addition and subtraction will be more complicated as compared to binary. Okay, so some disadvantages are there. First thing, that less number of bits required to represent the decimal number in binary compared to BCD. From this table, you can easily understand when you have a decimal number 10, the binary representation is 1010, it is 4-bit representation, but in case of BCD, it is 8-bit representation. And BCD addition subtraction also more complicated as compared to binary. Okay, we will do some BCD addition subtraction a little bit later. Before that, we will study another code which is known as gray code. Gray code known as the reflect binary code, reflected binary code. We call it gray code after Frank Gray, one of the physicists who has developed this code. After his name, this code is known as gray code, and also it is known as reflected binary code. It is unweighted code. In case of BCD, we have seen that BCD is a weighted code, positional weights are there, and it is 8421 code, but gray code is unweighted code. It is also known as unit distance code and minimum error code. 2 successive values differs in only 1 bit, which is very much important. Binary number is converted to gray code to reduce the switching operation. Binary number is converted to gray code to reduce the switching operation. Okay, so these last three points are very much important. I will show you what is the significance of these 3 points: unit distance code and minimum error code, how 2 successive values differ in only 1 bit, binary number is converted to gray code to reduce the switching operation. So these three I will explain. So you see, we have in the extreme left hand side, we have decimal numbers, the middle column representing the binary numbers, equivalent binary numbers, and the last column representing the gray code. Right now, I am not going to discuss how to convert binary to gray. I have written the gray code directly. I will show you how to convert binary to gray little bit later, but for this time being, you just understood what is the meaning of these 3 points. To see, okay, I will just show you. Okay. That would be better. I will take a particular example, decimal, binary, and gray. 3 and 4, 0, 0, 1, 1, 0, 1, 0, 0. And for gray code, it is 0, and 0, then 1, then 0, first 0, then 1, 1, 0, right? Yes, okay. Now you see, when you want to switch from 3 to 4, when we want to switch from 3 to 4, then in binary, you see how many switching you need in binary. If you just check this 0011 and 0100, only this MSB is not changing. In case of 3, the extreme leftmost bit is 0, and in case of 4, the extreme leftmost bit is also 0. So there is no switching. But if you see this bits, if you see this, and if you see again this, when we are trying to switch from 3 to 4, we need to switch in the 3 positions, right? Isn't it? We need to switch in 3 positions. Okay, I'll explain again. 1 minute. Okay. So I will write the positions. Suppose, okay, better I'll write it here. Okay. So we have B3, B4, 1 minute. B3, B2, B1, and B0, and we have G3, G2, G1, and G0. Okay, and we have decimal. This is binary, and this is gray code. Right. So in decimal 3, we have 0, 0, 1, 1. For 4, we have 0, 1, 0, 0. For gray code, we have 0, then 0, then 1, then 0, then 0, 1, 1, 0. Okay. So when we want to switch from 3 to 4, okay, you see, in case of binary, in B3 position, there is no switching. In B3 position, for 3, we have 0, and for 4, we have also 0, so we don't need any switching in case of binary. But if you observe in the B2, B1, and B0 position, when you want to switch from 3 to 4, you need to switch 0 to 1 in B2 position, 1 to 0 in B1 position, 1 to 0 in B0 position. So more switching is involved in binary, isn't it? Do you have any doubt in this? Just tell me. When we want to switch from 3 to 4 in decimal, you know what is the equivalent binary representation of 3 and what is the equivalent binary representation of 4. The 3 represented by 0011 and 4 represented by 0100. Now look at the positions. Extreme left position, which is the B3 position. In B3 position, for 3 there is a 0 and for 4 there is also a 0. So there is no switching. But in B2, B1, B0 position, if you see very carefully, in case of binary, there is a switching operation involved. Because when we are switching from 3 to 4, okay, in case of binary, if you observe very carefully, in B2 position, you have to switch from 0 to 1. In B1 position, you have to switch from 1 to 0. In B0 position, you have to again switch from 1 to 0. Then only you will get the binary equivalent of 4, isn't it? Okay, so this is about the binary. In case of binary, more switching is involved. But in case of gray code, if you just see the gray code, in position G3, you see there is no switching. In position G1, you see there is no switching. 1, 1. In case of G0, you see there is also no switching. 0, 0. Only in case of G2, you have a switching from 0 to 1. So if you compare binary and gray code, when we are switching from 3 to 4, how many switching required in case of binary? 3 switchings in B2, B1, B0 positions. But in case of gray code, you need only 1 switching in the G2 position. Okay, so from here we can write in binary, we need 3 switchings in B3, B2, B2, B1 and B0 positions. But in case of gray code, we need only 1 switching in G2 position. Okay, so do you have any doubt in this? So this point has been verified. Binary number is converted to gray code to reduce switching operation. This point has been verified. Do you have any problem with this? Please answer me, otherwise how could I understand you are getting or not? Is that okay?
Yes, sir.
Okay. Now the third point is we have explained binary number is converted to gray code to reduce the switching operation. Now second point can also be explained. 2 successive values differ in only 1 bit. Okay. Now if you see the gray code, this gray code, okay, I'll again write. For 3, 0, 0, 1, 0. For 4, so 2 successive values differ in 1 bit. 2 successive values 3 and 4 differ in 1 bit. where it has been deferred. Only this, you see in the G3 position, for 3 and 4, you have 0. In the G1 position for 3 and 4, you have 1 and 1. For at G0 position for 3 and 4, you have again 0 and 0. Only in G2 position, it has been varied. Okay, that is why it is written two successive values differ in only 1 bit. Okay, only 1 bit. Here in G2, in 1 bit, it has been differed. It is the 3 and 4, these are two successive values. In the gray code, it differs in only 1 bit. Okay, in G2 position, in case of 3, in G2 position there is a 0. In case of 4, in G2 position there is a 1. So this is only difference in 1 bit. Okay. Now we will see, and also if you see 7 and 8, then also you can understood same thing. You just take 7 and 8. In case of decimal, B3, B2, B1, B0, and in case of gray code, G3, G2, G1, and G0. In case of 7, you have 0, 1, 1, 1. In case of 8, you have 1, 0, 0. And in case of gray code, you have 0, then 1. And I think 0, 0. 0, 0. You have 1, 1, 0, 0. Right.
So will it be decimal or binary?
1 minute. 1 minute. What is your question?
In the heading, it is decimal or binary.
Oh, sorry. I have done some mistake. Yeah. Thank you. This should be binary. This is decimal. Okay. Yes. So you see, when you want to switch from 7 to 8, in case of binary, you see, in all 4 positions, you need to do switching. In all 4 positions, B3, B2, B1, B0, you need switching. But in case of gray code, you see only in G3 position you need switching. But for G2, G1, G0, you don't need switching. So in case of binary, you need 4 switching. Right? In case of gray code, you need only 1 switching. So when we are converting binary to gray code, automatically we are reducing the switching operation. And for the successive 2 values, 7, 8, if you see only the gray code, only this part, if you see only this part, you can understand the 2 successive values differ in 1 bit. Only G3 position, the bit has been deferred. For 7, in G3 position there is a 0. For 8, in G3 position there is a 1. Only this difference. Only difference in 1 bit. And rest of the things, G2, G1, G0 are same. Okay, so this is the gray code. Now we will study how to convert binary to gray. So we have B3, B2, B1, B0, then G3, G2, G1, G0. Suppose in binary we have 0, 1, 1, 0. So in case of gray code, what is the formula? G3 will be B3, G2 will be B2 exclusive or B3, G1 will be B1 exclusive or B2, and G0 will be B0 exclusive or B1. Right. So G3 will be B3 means 0. G2 will be B3 exclusive or B2 means 0 exclusive or 1. So you will have 1. G1 will be B2 exclusive or B1 means you will have 0. And G0 will be B0 exclusive or B1 means 0, 1 exclusive or means 1. 0, 1, 0, 1. You see, if you see this table, what we have taken? 0, 1, 1, 0 means 6, right? 6. This 0, 1, 1, 0 and the equivalent gray code is 0, 1, 0, 1. See? 0, 1, 0, 1. Okay. So you have to, G3 equal to B3 means you have to keep MSB as it is, and the rest of the bit can be calculated by the XOR operation. Okay. So I will show you again. Okay. Now B3, B2, B1, B0. So this B3 directly converted to G3. So this is the MSB, most significant bit in binary. This is the MSB in gray code. So MSB, you have to keep MSB as it is in binary and gray code. Okay. And then you have to take B3 over here and you will do exclusive OR operation, XOR operation. B2 and B3. B2 XOR B3, this gives you G2. Then B2 XOR B1, this gives you G1. Then B1 XOR B0, it gives you G0. So this is the gray code. Okay. Any doubt?
Sir, what is this MSB?
1 minute, I will tell you. Let's just give you one. What is your question?
What is this MSB?
Huh?
MSB.
Most significant bit. The leftmost most significant bit has the greatest numerical value. That already I have told you. Already discussed. Most significant bit. So the most significant bit in case of binary and gray code are same. So you have to keep MSB as it is. Whatever MSB you have in binary, for gray code, same MSB you have. G3 equal to B3. Like G3 equal to B3. Okay. G3 and B3 all are MSBs. These are MSB. G3 is MSB in gray code. B3 is MSB in binary. Then the next lower position bit can be find out by XOR operation of B3 and B2, and then G1. Then the next lower position bit G1 it can be obtained by XOR of B1 and B2, and then the LSB, this is G0 is what? LSB, least significant bit. That can be find out by B0 XOR B1. Okay. So do you have any doubt? Anyone? Any doubt you can ask me. Any doubt? You can ask me. Everything clear?
Yes, sir.
Okay. So we will take some another examples. Some other examples. So in general, we can write Gn is equal to Bn. This is for MSB. Here I have taken four bits. Now, if you have 5 bits, 6 bits, 7 bits, then what you will do? That is why I am just generalizing this formula. Here I have taken 4 bits in case of binary. That is why you are getting 4-bit gray code. But it is not necessarily that always you have 4-bit binary number. It may be 5 bit, 6 bit, 7 bit. So in that case, I am going to write the generalized formula. Gn is equal to Bn. It is for the MSB. Gn minus 1, the next lower position. This is Bn minus 1 exclusive or Bn. Gn minus 2, this is Bn minus 2 exclusive or Bn minus 1 dot 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 G1, that is equal to dot dot dot, okay, that is equal to B1 exclusive or B2. Okay, in general form. If small n is equal to 7, what will happen? G7 is equal to B7, G6 is equal to B6 exclusive or B7. So you just put the value of n, you will get your particular gray code. Okay. Now, another example, if you have in binary 1001, so what will be the equivalent? Great. Okay, so in case of binary, we have B3, B2, B1, B0, and the number given is 1001, 1001, and you know what is the formula of gray code. In case of gray code, G3 will be equal to B3. So here I will write G3, G2, G1 and G0. So G3 is equal to B3, so you will put 1. Now G2 is what? G2 is what? B3 exclusive or B2. So what is B3? 1. And what is B2? 0. So 0 exclusive or 1. So it will give you 1. So 1. This is 1 exclusive or 0. It gives you 1. Then G1. What is G1? B1 exclusive or B2. So what is B1? You see B1 0 and B2 is also 0. So 0 exclusive or 0, it means 0. We will write 0 over here. G0, it is actually B1 exclusive or B0. You see, what is B1? 0, and what is B0? 1. So 0 exclusive or 1, so it will give you 1. So you will put 1 over here. So 1, 1, 0, 1. Okay, so this is the binary to gray. Okay, and what about gray to binary? Suppose in gray you have 1, 1, 0, 1. So how to convert it to the binary? So for binary, The same thing, the MSB will be as it is. The MSB will be as it is, which will be 1. And then what you have to do, you have to do exclusive OR of this and this. Okay. So exclusive OR of 1, exclusive OR 1. So you will have 0. So you have to do exclusive OR of these two. Then you have to do exclusive OR this two. So 0, 0 exclusive OR, it means 0. And again you have to do the exclusive OR of 1 and 0. So it will give you 1. So 1 0 0 1. Okay. Is that clear?
Yes, sir.
Okay. So here you see in this manner, the reverse process you have to follow. Okay. So gray to binary. Right. Okay. So we have studied the BCD and binary. Okay. And there is another code, that is the XS3. Sometimes known as XS3 code. Okay. So XS3 code means, okay, in decimal, BCD and XS3. So for decimal, if we have 5, the BCD representation is 0 1 0 1, and for XS3 means add 0 0 1 1. 3 means what? What is the binary representation of 3 or BCD representation of 3? 0 0 1 1. So add 0 0 1 1 to 0 1 0 1. Okay. 0 1 0 1 plus 0 0 1 1. Okay. What you have? 0, then 0, then 0, then 1. So 1 0 0 is the XS3 representation of 5. Okay. So I will make a table where I will show you the decimal, then BCD, then XS3, right? XS3 means if you have a decimal digit, then you just convert it to the BCD and then add 3. You will get a XS3. Okay. So 0, 1, 2, 3, 4, 5. So you have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1. Okay. Now what you will do? You will add 3. So for XS3, what you have? 0, 0, 1, 1. When you will add 3, what will happen? You have 0, 1, 0, 0. When you add 3 over here, what you have? You have 0, 1, 0, 1. When you will add 3, you have 0, 1, 0, 0. When you add 3 over here, 0, 1, 1. When you add 3 over here, 1, 0, 0. Again, you have decimal, you have BCD, and you have XS3. You have 6, 7, 8, and 9. So 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1. Right? So if you add 3, this will be gives you 1, 0, 0, 1. Because 6, it is 6. When you will add 3, you will have 9. You have 7. So when you will add 3, you have 1, 0, 1, 0. When you have 8, if you add 3, you have 1, 0, 1, 1. And when you have 1, 0, 0, 1 and you add 3, you have 1, 1, 0, 0. So this is the complete XS3 code. And if we just write down the decimal and XS3 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0. Okay. Now, one interesting thing, just give me 1 minute. One interesting thing you can observe, this XS3 code is actually self-complementing code. How it is possible? Okay. You see, this 2 value. For 0, it is 0, 0, 1, 1. For 9, it is 1, 1, 0, 0. Both are complement of each other. 0, 0, 1, 1, 1, 1, 0, 0. Right. Now, if you see 1, okay, and it is 0, 1, 0, 0. And if you see 8, it is 1, 0, 1, 1. So 0, 1, 0, 0 and 1, 0, 1, 1, these are complement of each other. Same thing you can see over here. The 2 is 0, 1, 0, 1. And you see 7 is 1, 0, 1, 0. 0, 1, 0, 1. And then you have 1, 0, 1, 0. So these two are complement of each other. Similarly, 0, 1, 1, 0 and 1, 0, 0, 1. These are complement of each other. And again, you have 0, 1, 1 and 1, 0, 0. So these are complement of each other. That is why XS3 code is known as self-complementing code. XS3 code is known as self-complementing code. Do you understand what I am trying to say?
Yes, sir.
Is that okay now? Any confusion? 0, 9, 1, 8, 2, 7, 3, 6, and I think 4, 5. These are complement to each other. When you will represent 0 in XS3 and you will represent 9 in XS3, these two complement of each other. Similarly, when you represent 4 in XS3 and when you will represent 5 in XS3, these two complement of each other. That is why it is known as self-complementing code. So I'll stop here. In the next class, I will show you how to add and subtract in BCD. Okay, give me the attendance in WhatsApp. Send me that.
Thank you, sir.
Thank you, sir.
Thank you, sir.